The intermediate value property, let's have a look at this then. Let f be continuous on the interval ab. For every real number gamma between f of a and f of b, there exists a number c in ab such that f of c equals gamma. So, what does that mean? Let's have a look at the picture. But first there's a commentary. This result claims that if f is a continuous function, f takes the value f of a and f of b at the endpoints of some interval a and b, then f must take all possible values between f of a and f of b. Sketch the case where f of a is less than f of b. So let's have a look at the sketch then. Here it is here. So f is a continuous function, and it's saying defined on AB, and you've got an f of a where it started and f of b where it finished, and it's saying that for any point gamma in between these two, there will exist a c such that f of c equals gamma. So let's go back up and remind ourselves what that says then. So it says that just here, doesn't it? So f is continuous on this interval for every number gamma, real number gamma, between f of a and f of b. We can find a c such that f of c equals gamma. The c will lie between a and b. Okay, so that's what the intermediate value property says then. So let's just go down the page and look at the proof. And we'll start the proof now. So we prove this result when f of a is less than gamma is less than f of b, and a is less than b. The corresponding proofs in the other cases are similar. So we're going to assume that f of a is less than f of b, gamma lies between, and of course a is less than b in the interval. The corresponding proofs in the other cases are similar. The essence of the proof is to consider the set of x's for which f of x is strictly less than gamma, and show that if c is the supremum of this set, then f of c is equal to gamma, with c in a, b. So let's have a look at that then. So let S, the set, be all the x's in a, b where the f of x's are less than gamma. We know that gamma is a value that we've chosen between f of a and f of b. Okay, and we've got this set S that corresponds to these values of all the x's in a, b, such that f of x is less than gamma. Now the set S is non-empty, is it? Well, let's have a look. Does it contain a? Well, if we put a in here, is a in ab? Yes, it is. And is f of a less than gamma? Well, yes, it is by this condition here. So a does in fact belong to S. So S is non-empty. And it is bounded above. Clearly, it's bounded above by this restriction here. It can't be any bigger than b by this simple restriction here. So it's non-empty and bounded above. Hence, by this completeness axiom then, for real numbers, S, the set S, possesses a least upper bound. So we'll let C denote the supremum of the set S, then the least upper bound. Then, clearly, because of this restriction here, C must lie between this range, between A and B. In fact, it says, the proof goes on to say, the condition C is between A and B holds true. So to see why this is the case, note that since f is left continuous at A, f is continuous on the interval AB, so it's clearly left continuous at A. For epsilon equal gamma minus f of A, gamma minus f of A will be greater than 0 from here. So that's fine. So for that epsilon then, there exists a delta sufficiently small so that the a plus delta are still in the set AB, such that if x lies in here then, using left continuity, then the f of x's will have this inequality. And x in this range, well this value of x is certainly in that range, isn't it? A plus half delta is in here. So f of a plus half delta minus f of a is less than epsilon. That's fine. And so f of a plus half delta then, here, just this, we'll take the positive part of this modulus, is less than epsilon. And the epsilon we can put in is our value gamma minus f of a. We can cross off the f minus f of a's, and we just simply see that f a plus half delta is less than the gamma. And as such, a plus half delta then is in S. Because a plus half delta is clearly in AB, the way we defined the delta. So a plus half delta is in here. And also f of a plus half delta is less than gamma, which is what we've got down here. So that definitely is in S then. This means that the supremum of the set C, if a plus half delta is in S, then a value bigger than A is in S, so the supremum of this set must be bigger than A. So C, the supremum, then must be bigger than A. So that's that part. Now the next inference is here. To establish that C is less than B then, which we also need to show, let epsilon equal FB minus gamma. Now that, if we look back up, FB minus gamma is positive, so this is positive. Then the right continuity of f at B now guarantees there exists a delta, sufficiently small so that B minus delta is still in AB, of course, such that if we look at the right continuity at B, if x is in here, then the f of x's will obey this inequality. And if you look at B minus half delta, well, that's clearly in this region here, isn't it? B minus half delta. So it will satisfy this inequality. So this is less than epsilon. And then, because it's a modulus, we can flip the modulus value around and write this first and that second here. And that will be less than epsilon. And epsilon is FB minus gamma. So that's that. Then what we can do is cancel the FBs. There we go. And then times that by minus. We get that. This will flip around to that, positive. And this will become gamma. So FB minus half delta is greater than gamma. And so B minus half delta is not, because it's bigger than gamma, B minus half delta is not in S, is it? Because it's not less than gamma, it's greater than gamma. So delta may be chosen arbitrarily small as we wish, with values approaching 0. So this B minus delta is a whole array of points that go right down towards B, from B minus half delta here. So here's A and B. And B minus half delta, say, is here. And that delta was greater than 0, wasn't it? But any smaller delta also. So anything, any value along here towards B itself is also, satisfies what we've just said. And so none of these points, if this one doesn't belong to S, then we just can infer straight away by the epsilon delta definition arrangement that any smaller delta also will be sufficient, and so this similarly will be bigger than gamma. So all of these then, for any delta greater than 0 that's less than this particular delta, is not in S. So delta may be chosen as arbitrarily small as we wish, with values approaching 0. So right up to B itself then, since the isolated point B itself is also not in S, we conclude that C is less than B. So not only is all these points up to B not in S, we also claim that B is not in S. Now, is that the case? Well, the point B itself as that single point, that's not in S. And why is it not in S? If we look here, B is in here, but for it to be in here, f of B would need to be less than gamma. And here we've got f of B is greater than gamma. So B as a singleton is not in there. Okay, that endpoint is not in there also. So clearly then, what does that tell us? Just gone a bit too far. We conclude that C must be less than B. So the supremum then of S cannot be B, because not only was B not in, but all the points before B up to here were not in. So the supremum of that set S must be away from B itself. So C is less than B. So now we've got this inequality, and we'll go on to the second part of the proof, using this fact in the next part 2.